I don't know. I mean, I, I think I probably would have started finding students if I was regularly teaching the math major classes there, but like, I just couldn't in good conscience like ask for any of those classes to teach because there's hardly any work to do, right? So like if I'm taking that from somebody, I'm basically, what do they do? I don't know. So.
It's record, I mean, so.
Yeah, I guess so.
You just got time to throw me a bone.
So anyway, I'll begin with a word of prayer. So dear Heavenly Father, we thank you for this day. Just pray that you guide our steps, help us to understand a little bit more about the algebras, Lord. In the name of my prayer, Lord Jesus. Amen. Okay, so yeah, Schur's lemma. We got hung up on this because I was like sleepy and stuff. And I think we have one direction of this pretty well proved the other time. The let's see here. So I'm gonna look at the direction the book gives more details on this time. All right, so suppose theta is an L-module homomorphism. All right. So suppose theta is an L-module homomorphism, all right? So that means it's a linear map of a complex vector space. All right? And then he says, so it must have an eigenvalue, say lambda. So that's, I think, a theorem from linear algebra. If you have a linear transformation on a complex vector space, you have an eigenvalue, right? Now that's not true for a real map, but it is true for a complex map, right? Like the real map that fails because, for example, like rotations in the plane, you've got no eigenvalues, right?
Yeah.
But we don't face that trouble in the complex case. There's always an eigenvalue. So let lambda be the eigenvalue of theta, all right? And so that means that we can look at theta minus lambda times the identity on S, all right? All right, now, so theta is a linear map, and if you subtract a scalar multiple of the identity on S, well then it's also a linear map, right? So what do we've got, in fact, more than that, it's an L-module homomorphism. What would that mean? That means it satisfies the, the definition of L-module homomorphism. So that was given, I guess, back at 7.6, right?
Yeah, I mean, the L-module homomorphism is just like exactly what you would think it is. It's the map is what you can. If you put a multiplication or an operation in, you can get the map of the operation out, and the other condition is.
Yeah, he's.
Escaping me. That's the point.
Let's see, it's a linear map such that, so he has like theta of x dot v is equal to x dot theta of v, right?
Yeah.
But
Equals scalars out and it's linear, essentially. Or like not linear, but you can like theta of x dot y is equal to theta of x theta y.
yeah, I guess right. Question is, what does dot mean, right? So, So that goes back to, goodness gracious, back to 7.4, I think. Goodness gracious. Do I need to go back to the... Sorry, Audric. So to start with, the representation... Chapter 7 starts, right? A representation L of a Lie algebra is a homomorphism from L to GLV. All right. So remember, we start by preserving the abstract bracket in L to the commutator bracket in GLV. And let's see here. Now this dot, this Lie algebra, the L module action, right? It has to satisfy axioms M1, M2, and M3 on page 55. Namely that, like M1 and M2 are like linearity, but the more interesting one, of course, is this one, x comma y. Well, more interesting to me, x comma y dot v is equal to x dot y dot v minus y dot x dot v, right? And that's for all x and y in L and v and w in v. All right, so the idea, and of course, the idea is that the Lie algebra is acting on a vector space. In the application to quantum mechanics, the vector space is like the state vectors, and the Lie algebra is the algebra, the symmetry group of the quantum mechanics that we're talking about. But we'll get there. So, but here, let me stay in this course. All right. So, I just want to. I mean, he says it's an L module homomorphism. Let me just check on that, because I think checking on that will kind of force me to get where we need to be in terms of understanding what we're doing. So claims that theta minus lambda times 1 is an L module homomorphism, right? So it's clear enough it's linear, right?
Yeah.
And let's see here. The S is the irreducible representation. I believe S plays the role of V down here. So we should look at, theta minus lambda times 1 on S. We let that act on sorry. Anyway, so this when it acts on x dot v is supposed to be equal to x acting on, well, in this case, theta minus lambda times the identity on S, acting on V. Well, all right, so
theta minus lambda 1s, that should be acting on, let's see.
oh yeah, this should be by definition like theta x dot v minus lambda 1s on x dot v, right?
Yeah.
But then theta is given to be an L module homomorphism, so the thing I'm a little bit, I'm not, sorry, Audric, I'm a little apprehensive here because I'm not sure what the dot means. Well, he says at the start of 7.3, An L module for L, or alternatively an L module, is a finite dimensional F vector space together with a map, which we denote by the dot. Now that's a, well, that's an L module. We have, in our current application, we're looking at an L module homomorphism, which plays together with an L module, I guess. Yeah. All right. And then currently, Schur's lemma, L module homomorphism. Yeah. All right. Okay. Sorry, Adric, I'll eventually get it. Now this is, so since we're assuming that theta is an L module homomorphism, this must be the theta of x dot v, right? And then over here, this is literally minus lambda x dot v, right? Because that's what the identity does. And then my properties of the module action, the L module action, we can factor out the v. All right. So we've got theta x minus lambda x dot v. Here I'm using one of the linearity modules of the L module action, right? That's like either by M1 or M2 on page. What was it? I think I'm technically using M2 on page 55 at the moment, all right, to make that step. Now, next step, this literally is theta minus lambda times the identity on S, acting on X, all of that dotted with V.
You can drop the,
That's funny. Whoa. Is that right? X dot V. Whoa. Oh, I did this wrong, Audric. I'm sorry. I'm a dummy. Look, I haven't followed my own definition. See what happens here? Right here. So theta of x dot v is x dot theta of v, and I flip-flopped it. This is just nonsense. It doesn't even make sense. All right. What I just wrote, that doesn't even make sense. It should be the x theta of v. That makes sense because it might have also made sense the other way. I don't know. I don't think so, though. But this theta of v is an element of S again. So we're looking at something in L dot something in S. And, OK, this is fine. But then I want to I guess it might have been M. I guess it's M3 I needed, not M2, right? Well, M1. Right, so x dot parentheses theta of v, what did you say?
Would the same thing apply to the lambda, or is the lambda a different mapping?
The lambda is just a constant here. It's a scalar. It's the eigenvalue. Oh yeah, yes. But it's the identity map on V. So, excuse me, the identity map on S. We had better be operating on S, right? X is an element of here. X is in the Lie algebra, and V is in the in S, I believe, in our current context. So theta should only be acting on, like x dot v is again in S, right?
Yeah.
Okay, so all right. So then this is x dot theta minus lambda times the identity on S acting on V. Which is that is in fact, of course, the actual identity that we want, right? So that shows, well, that's part of it, right? That shows that, that's part of, is that all that's needed to show it's an L-module homomorphism? Maybe.
Let's talk about kernel.
Well, I'm just saying to,
Oh, yeah.
what's the definition of L-module homomorphism? It's back on page 60. Theta of x dot v is x dot theta of v. Okay, so yeah, we got it. That shows that it's an L-module homomorphism. All right, great. And, all right, so it's an L-module homomorphism. And what we argued last class was that if you have an L-module homomorphism from an irreducible L-module to an irreducible L-module, it's either the zero map or what?
Linear?
I think it's either the zero map or it's the identity, if I remember right. There's no...
Oh, yeah.
there's no because there's no non-trivial...
Yeah, that's right. There's no non-trivial...
because the image... Right. Because the image is a submodule and the kernel is a submodule, so it forces either the image to be everything or the kernel to be everything. Those are your only... Because otherwise you'd have a non-trivial submodule of an irreducible, and you can't have that. So, okay, so then, all right, so then look at the kernel, but consider the kernel of theta minus lambda times the identity. What can we say about that? Notice that the eigenvector of theta is in this, right? It contains, let's say, V in S such that theta of V is equal to lambda V, certainly, right? So that tells us that the kernel is what? It's not equal to the set. It's not equal to just zero. What contained in S? What do you say?
Well, wait. How can that? Oh, that's the kernel. I guess that's what this was mapping everything to zero.
Right. But my point is that a particular vector that's mapped to zero by this map is the eigenvector that we know exists. Right? So since the eigenvector exists, that means that the kernel is not the zero set. It contains at least one. It contains at least one non-zero vector. But being that S is an irreducible, an irreducible L module, we're stuck with the kernel being the whole thing, right? So therefore, the kernel of theta minus lambda times 1 is in fact equal to S, right? Which is another way of saying that theta minus lambda times 1 on S is equal to the 0 on S, right? Which is another way of just saying lambda, theta is 1 times the, so there you go. We have shown that theta is a scalar multiple of the identity on S. So. All right, let's look at some of the applications of Schur's lemma that we still have in chapter 7 to look at. So like, I'm gonna erase this if that's okay.
Yeah.
The coach has actually started letting Isaac pitch in the baseball. Isaac is like on the top of the world.
Let him pitch.
Yeah, let him pitch.
I'm not a big fan of pitching myself, but
It's it's very unnerving. I mean, it's
Yeah, I like the ball getting hit right back at me.
it is difficult. Yeah, the ball getting hit back at you. It's
And then not only that, my arm hurts.
oh, that is that will happen.
No, just like just throw as hard as you can, and just
Right. Yeah, over and over again. And then the other aggravating thing is like the officiating in terms of like umpires. It's just very,
yeah.
very sketch, both for the hitters and the pitchers. I mean, it's just, sometimes it really feels random to me.
I liked I played in the infield, but yeah, I was never a fan of his. I've seen people slow pitch softball get just drilled. So like the pitchers. So like I'm not a fan.
Hmm. So,
Baseball player to watch this lecture one day. But
so L a complexly algebra and V an irreducible L module. All right, if Z is an element of the center of the Lie algebra, right, then Z acts by scalar multiplication on V. That is, there exists lambda in the complex numbers for which such that Z dot V is equal to lambda V for all V and V. All right. It occurs to me we haven't defined what irreducible module means today. Probably would be healthy for me to remind what that means. Lie module V is said to be irreducible or simple if it's non-zero and it has no submodules other than 0 in itself. Of course, we just used that in the proof, but anyway. All right, so the proof of Lemma 7.14 is relatively simple. Let me write it out here. You remember what ZL means?
the center.
It's the center. Yeah, but what was that?
Anything that's like what, commuting?
Right, it's, yeah, exactly, X and L, such that the commutator of X and Y is equal to 0 for all Y and L, right? So it's the set of elements in the Lie algebra that commute with all the other elements, right? So here's the proof of this lemma. He says, consider the map V maps to Z dot V he says, what's his dot? Okay, okay. Irreducible L module, right? So we have a dot to work with, all right? Is an L module homomorphism? I'm sorry, it's weirding me out here. All right, well, let's look at the calculation. I think the calculation will clear up what's going on here. So Z dotted with X dot V is equal to X dotted with Z dot V plus the commutator of Z and X dot V. All right, I think I need to write out something before I say more. So the M3, right? M3 said what? M3 in the definition for L module action said that if we take the commutator of like x and y and we let it act on v, then you had x dot y dot v minus y dot x dot v, with the parentheses, of course, appropriately supplied here. So what's going on in this calculation down here is he's putting y to be z, right? Y is z, and all right. So if we solve that for the like first term, no, wait a minute. Well, so this would say that z dot x dot v is equal to x dot z dot v minus x comma z dot v if I solve that. So you've got z dot x dot v equals to x dot z dot v plus, well, you notice that here, see what's going on?
Yeah.
This is, of course, this is minus z comma x, so if we flip it, we get to that. Why is that an L module homomorphism, though?
I see. No, yeah.
Why does that rule define an L module? I mean, where is z dot v? I guess it's L module, so it's going from v to v, I guess. V is an irreducible L module. So I'm assuming that the dot, right? The dot here is a mapping from what? From L cross V to V again, right? So if I call this map theta, right? We've got like theta of V equals to z dot v, right? And I suppose that makes, it makes sense. It's theta is going to be a mapping from v to v, right? Okay, so yeah, it's at least a linear map, right? It's a linear map.
Yeah.
Is it an L module homomorphism? To be an L module homomorphism, we need to satisfy what condition? So it needs to be linear, and we also, yeah, what is it? Is how's it go? X dot theta of v equal to, oh man, I've already forgotten this. I should not have erased it. Good grief.
Yeah, oh wait, that's x dot theta of v is equal to theta of x dot v.
Almost. You might have said it, I may just not heard it right. So theta of x dot v is x dot theta of v, right?
Yeah.
So it's linear. And then this, of course, this is 0, right? Because z is in the center. So what we have here is x dot z dot v. Of course, what is this calculation here tantamount to saying? It's saying that theta of x dot v, right, is equal to x dot theta of v. Do you see it? Like, the definition of theta is z dot the thing, right? So here we're doing z dot this thing. So this right here is literally theta of x dot v, where theta is as I've defined it right here. And then we have x dot z of v, z dot v, which is again x dot theta v. So this altogether shows that theta so defined is in fact a L module homomorphism of v, and v is a irreducible L module by assumption, right? Okay? So now we can apply Schur's lemma. And what does it tell us? So Schur's lemma says that this theta has to be equal to lambda times the identity on v, right? And so, of course, if we look at theta of v, we've got z dot v, right? But we've also got lambda times v, which is exactly what we were trying to prove. So if we have an irreducible L module and we look at the action by the center, it's just scalar multiplication. All right. He says a corollary of the previous lemma is that the simple L modules for an abelian Lie algebra are one-dimensional. Simple modules for an abelian Lie algebra are one-dimensional. We deduce this as follows. Suppose that V is a simple module for an abelian Lie algebra L. By this lemma, every element of L acts by scalar multiplication on V. And so any non-zero V spans the one-dimensional submodule of V. As V is irreducible, the submodule must be all of V. Oh, okay. So if we have a simple module for an abelian Lie algebra, they're just one-dimensional. It's essentially a corollary to this lemma 7.14. So, and then, let's see here, remark. In chapters 5 and 6, we worked with the hypothesis that a Lie algebra L was a subalgebra of GLV for some vector space V. In other words, we were assuming that L had a faithful representation on V. Although we did not prove it in this book, it is a theorem, Adu's theorem, that every Lie algebra has a faithful representation. So if L is a Lie algebra, and let me write this down here. So if L is a Lie algebra, and we have phi representation from L to GLV, all right, then we can apply results of chapters 5 and 6 to the subalgebra image of phi, which is a subalgebra of GLV, all right? And so, in particular, it makes sense to talk about weights and weight spaces for L. So basically what he's saying here at the end of chapter 7 is that it's not unreasonable to think of a Lie algebra as a set of linear transformations on a vector space. Because even if the Lie algebra is not, at the start of things, a set of linear transformations on a vector space, it's possible to find a faithful image of that algebra as a subset of linear transformations on a vector space of an appropriate size.
Oh yeah, I thought it said not necessarily faithful.
Right. Let's see here. Well, yeah, for that paragraph. But in fact, well, yeah. I mean, I guess even if it's not a faithful representation, you still gain information about the Lie algebra from looking at the image of that representation. But okay, anyway, so this brings us to chapter 8. All right. So I think I got about 15 minutes or so here today left. Can I erase?
Yeah.
Okay. So chapter 8 is on SL2C, representations of SL2C. I think we've got just about enough time to do the calculation at the start of the section. So that's a good thing for us to start on. So let's see what we can do with that. So let's see here. Let me read his preamble. In this chapter, we'll study finite dimensional irreducible representations of SL2C. So which I think is kind of an oddly specific thing, isn't it? We've been doing these more abstract kind of arbitrary modules, arbitrary Lie algebras, and all of a sudden we have a whole chapter devoted to representations of just this one particular, one particular three-dimensional, Lie algebra here. I know it's kind of funny, right? But it's important because this fundamental example is at the root of many things. So, he says, in doing this, we shall see a stripped-down form many of the ideas needed to study representations of an arbitrary semi-simple Lie algebra. And later we'll see that the representations of SL2C, in fact, control a large part of the structure of all semi-simple Lie algebras. So remember SL2C, we can look at as the span of E, F, and H, where E is 0, 1, 0, 0. F is 0, 0, 1, 0. And H is 1, 0, 0, minus 1. Of course, these are traceless, right? All right. So he says, we'll begin by constructing a family of irreducible representations of SL2C. All right. And now for something different. So consider the vector space of polynomials in two variables with complex coefficients. And all right. So we're going to consider complex polynomials with variables x and y. And he wants v sub d to be the subspace of homogeneous polynomials in x and d of degree d. All right, great. So V0 is just the constant polynomials. I'll just say constants, all right? And, well, he says, he jumps straight to VD, great, as, of course, x to the power d, x to the power d minus 1, y, x to the power d minus 2, y squared, and so forth, all the way up until, like x, y to the d minus 1, and y to the d, all right? But it's linear combinations of these guys, right? So homogeneous means every term is like, of that degree. I think probably the most familiar sort of thing like this is our discussion of quadratic forms in the other course, right? Those are homogeneous degree 2. Now, what's the dimension? So if you just track this formula here, right? We've got like x to the power d, all the way down to x to the power 1, and then one more. So if you do count this, the dimension of VD is d plus 1 as a complex vector space. Oh, he says we're going to make V sub d into an SL2 module by specifying a Lie algebra homomorphism. So VD is SL2C module according to phi, which is going to be a mapping from SL2C to GL VD. And he says, and of course, if you can, it suffices to define phi on E, F, and H, right? Since that's a basis for SL2C. All right. And so we would like to define operators on VD which behave as E, F, and H, all right? So, all right. Fine, I'll follow the book, which is by no means motivating any of this, right? I mean, this is like, just, I mean, what? So anyway, here we go. So phi of E is going to define to be x times the partial derivative with respect to the y variable. Perfectly, and that's reasonable. That is, in fact, of course, a linear transformation on VD. How do I know that? Well, if you take the derivative of a, bivariate polynomial of homogeneous degree d, you get a bivariate homogeneous polynomial of degree d minus 1. But lo and behold, we are multiplying by x, which gets us back to degree d. So indeed, we go from VD to VD. Woohoo. All right. And so I guess once you write that down, it's not too surprising that the definition for the mapping of F just interchanges the roles of y and x. Because after all, isn't that what the matrices that fundamentally represent E and F do as well? I mean, they do, right?
Yeah.
E is to F as X is to Y. And then, phi of H definition is X partial X minus Y partial Y. Now I start to see a pattern. I start to feel like if I had, other kinds of matrices, maybe I could play this game with those as well, But neat. So, and he says, well, his initial point is that the phi h acts quote unquote diagonally on VD with respect to our chosen basis. And the theorem is that with these definitions, phi is a representation of SL2C. So let me begin with the diagonally claim. So note, VD is in fact equal to the span of, complex span of course, of x to the power I, y to the power j, such that 0 is less than or equal to I comma j is less than or equal to d, and I plus j is equal to d, right? That's just a fancy way of writing this list. Like that. So anyway, a typical basis element is exactly what I have written. So if we take phi of h and we let it act on xi, yj, right? Well, that's x partial x of xi, yj minus y partial y of xi, yj, which is equal to I x I minus 1 yj minus y. Oh, I forgot my x. Ix. My bad. I is not an imaginary number here either. Minus y, excuse me, xi j yj minus 1. And that is, you know, I minus j times xi yj. Now, I suppose, to be clear, I'm assuming for that calculation's purpose that I and j are both, you know, greater than or equal to 1, right? In the context that either I or j are 1, if I is 1, then j is d, in which case, excuse me, if I is 0, then j is d. And so if I is 0, that means that there is no x dependence, which means this term drops out, and you're just left with minus y times d, y to the d minus 1. So you literally get minus dy. And so the formula is still true in that case, even though the calculation that I've written here is bogus. Like it's still legit. When I equals to 0 and j equals to d, this does give you minus d when you run through it. Likewise, if we think about I equals to d and j equals to 0, we'll get d x to the d, and the y term just goes away. So again, the formula is legit. So the calculation really, I think, only makes sense, technically speaking, when I and j are both, you know, 1 or bigger. More to the point, when neither I nor j are 0. But in the fringe cases, the formula still works. So cool. Anyway, so that obviously shows you that phi h acting on the basis is just multiplication by a number, which is to say that if you were to look at the matrix of phi h, right? The matrix of phi h, what would it look like?
The matrix of phi h would be would it be partial x and the 1, 1, 0, 1, 1, 2, 2, 1, 0, and then partial y minus partial y. And
Yeah, so if I, assuming I use this as the ordering of my basis, right? Like the d, it just gives you d minus 0, so it gives you like d here, right? And then this one gives you what? d minus 1 minus 1. Oh, is it always d? It's always d. I think it's always d.
yeah, that makes sense.
So I could be wrong, but
No, because you're adding, no, because I goes up.
maybe I'm wrong.
J goes down.
Is it just a quirk, a coincidence of the? Well, then here I get d. Oh, wait a minute. Yeah, I get d minus 2 minus d minus 2 minus 1. Oh, wait a minute. Oh, I'm bad. I'm dumb. So it goes. This one actually. What would you say? It was d minus 2, wasn't it?
Yeah.
So it's, oh, so it's not D, it's D minus 2. Thank you. And then I guess the next one would be
D minus 4.
D minus 4. And so on all the way down until eventually you get to y sub d, which is just minus d, I believe. Yeah.
Wait, but if you have 1 minus d minus 2, I'm sorry, minus d minus 1, it would be minus d, and the 1's cancel. No, the 1's wouldn't cancel. It'd be minus d plus 2.
Oh, that one's 1 minus parentheses d minus 1, which is
minus d plus 2.
minus, yeah. So that's kind of what you're expecting, right?
Yeah.
So it's like decreasing by 2 all the way down from d all the way to minus d. And this is a d plus 1 by d plus 1 matrix, right? I don't think the book's even talking about it. I'm just talking. You be quiet. You be quiet. Shush. Shush. Cool. All right, well, this is where we'll start next time. Sorry I'm out of time. So, I'm really enjoying this section. It's so calculus-y. I think this chapter is going to be really fun. So hopefully tomorrow we'll.
Do you think next week you should get back up to quantum?
Yeah. Who knows? Maybe. Yeah. Maybe. If things go well here, maybe we'll get enough. If we meet enough this week on the Lie algebras, I need to get up through like the. If we meet enough this week, Lie algebras will get far enough that I can jump from the quantum mechanics to the talk I have that melds Lie algebras and quantum mechanics. I have some nice notes that I made for a talk in a representation theory course when I was in grad school, which we can use. They're the natural, it's the natural melding point between this course and the analysis course.
Okay.
It's actually really ideal what we've covered this semester. It's perfect, actually. But anyway, so tomorrow we'll try to do a couple hours of this, I'm hoping. So, all right?
All right, sounds good.
Sounds good. Talk to you later.
Yes, sir.
Excuse me.